Bismillahirrahmanirrahim. In this video, we'll talk about small signal model of semiconductor diodes. Now, we have learned that in case of an ideal diode, the characteristics is like this. That is, the moment we go to forward bias, the diode starts fully conducting. So this was the ideal characteristics. But in actuality, it does not happen. The actual characteristics curve is something like this. So this means that when there is a negative voltage or when the diode is in the reverse bias, there is a very small current which flows, this much you can see. And when the diode is forward bias, up to about 0.7 volt, very less current flows, and then it starts increasing suddenly, and the rate of increase is very, very high. So this is the actual characteristics curve. Now, before we proceed, a very important point we have to keep in mind. This is going to confuse you a lot. Keep in mind that when the sign is in capital letters, that is V is in capital and the subscript is also in capital, this represents a DC quantity, DC voltage in this case. When both of the signs are in small letters, then this represents AC. And when there is a combination that is small and capital, that is AC and DC. So this is a combination of AC and DC. So keep this point in mind. I'll keep on reminding as well. Now let's try to understand what is small signal model means. And you have to be very, very patient to understand this. What he's saying is there are applications in which a diode is biased to operate at a point on the IV characteristics curve. So this is the IV characteristics curve, and in that we select a point where the diode should operate. This is known as the bias point or Q point. And how we select is shown here. Now this is the battery and we have a diode connected, although we do not connect directly a diode, but just for explanation this circuit is given. So the current flowing through this and this voltage across the diode, we plot it here. So this is the voltage across the diode and this is the current flowing. So that is how we determine the operating point of the diode. And for this we have the equation that the DC current or the diode current is given by IS. We have learned in the previous video that this is the saturation current or reverse saturation current, and e raised to the power Vd is the diode voltage and Vt is the thermal voltage, which is assumed to be 25 millivolt, or in some books it is 26 millivolt given. Now, if we have this battery instead of a battery cell, if we let's say use a rectifier circuit to generate this voltage, then as you know the rectifiers will have ripples. The rectifier output will have ripples. Say let's say this is 10 volt, then around that there will be capacitor charge discharge. So this ripple, and this is what is introducing the variable signal or AC signal. So and now if we look at this graph, when I was a student I never liked this graph, but now I enjoy this. So look at this graph. We have selected a point here at the Q point and we have drawn a tangent line. So this line is 100% straight line, and we are assuming that this portion of the curve will also behaves like a straight line. And now this ripple that we have is kind of a triangular shape. So this is the input. We are taking just this part of the ripple here, and we're saying that if a small input signal is applied, then the output signal will be something like this, and it will be just a kind of a reproduction with some higher magnitude. Okay, so now our circuit, this can be represented as the DC voltage and the ripple voltage, or the AC voltage we can say, to give the correct picture. And so this voltage, now you can see across this or across even diode, is now a small v and capital D, that is AC and DC, combination of these two, DC and AC. And similarly, the current will also change. Now, no more it is DC, it is a combination of AC and DC, so small I capital DT. So the total instantaneous voltage across the diode, VDT, we described. This voltage is also across the diode, and it is summation of the DC and AC. And correspondingly, the total instantaneous diode current from this equation, will now write it as I D capital T, that is, this is the instantaneous diode current or AC plus DC current, is equal to this IS remains same, but the VD changes. This was capital V capital D, now this will become small v capital D, that is the combination, this voltage here, divided by Vt. And we know Vd is VDC plus AC, so we can write it like that. And then we can separate these, so it will be ISE V capital D over Vt into E VAC over Vd, or small v small d. And now if you look, this term here, from here, it is ID, so we can replace this by ID, capital ID. So I instantaneous or IAC-DC is equal to IDC e raised to the power VAC over VT. Okay, so we were here, and now we come to the small signal analysis. What we are saying, that if this VD is kept sufficiently small, that is, this voltage is very small, the condition is that it should be very small, then this term VD over VT, we can say it is very less than 1. And therefore we can now use this exponential equation, that is Ex is equal to 1 plus x over 1 factorial x square plus 2 factorial x square plus 3 factorial. And when x is very small, then we can neglect the higher power terms, and so it will be 1 over x plus 1. Same technique we can apply, because this, in our case, this term is also very small. So we can write it as ID 1 plus Vd over Vt, 1 plus x. So 1 plus Vd over Vt. So this is the small signal approximation. So this is small signal approximation, and this is valid for signal where amplitude is smaller than 5 volts. So this has to be less than 5 millivolt. Also, as I had mentioned earlier, that Vt is the thermal voltage, or voltage due to temperature, and this is 25 millivolt or 26 millivolt in some books. So this is fixed. And so from here, if we just open the bracket, we get this term, IDT is equal to ID plus ID over VTD. And this we can write as the superimposed of the DC current ID, the superimposed on the DC current ID, we have a signal current component, we call it I small d, directly proportional to the signal voltage. So this is due to the AC current, and so we can write it like this, that ID, we are just doing away with T, is equal to IDC, and this is IAC, or small I small d. And if we compare these two, we can write this term that ID is I d over Vt and V small d. And this term here is, we can call, is the conductance. I hope you know what is conductance. We know that R is V over I, and the conductance is opposite of that, that is I over V. So I over V is this is called the conductance for the small signal diode, and opposite of this, the inverse of this, will be called the incremental resistance RD. So RD will be just inverse of this, that is Vt over ID. Okay, the very important point here, that if you have a small signal equation, this analysis, small signal analysis, can be performed separately from the DC. So this DC is separate. If you want to find the AC analysis, you can just work it without the DC or turn off the DC. So we'll see this in the next example. And now we come to the graphical representation of this signal here. We'll revise this one more time. It is easy to see that using the small signal approximation is equivalent to assuming that the signal amplitude is sufficiently small such that the excursion along the IV curve is limited to the short, almost linear segment. So this signal is so small that this output current or the DC diode current, its excursion is also very, very limited, that is within this linear portion of the curve. This is the tangent, and this is also almost linear. The curve is also linear. Now the slope of the segment, we can write it from here. The slope, y over x. So I over d, I over id over vd. We can write it as delta id over delta vd, or curly id over curly vd, where id, that is I AC DC, that is the total current, is equal to id. So at this point, this is id, and the AC DC current IDC is also very close to this point. So when ID, that is DC AC, is approximately equal to IDC. And this is the small signal conductance, as we had mentioned earlier also. And now the resistance is 1 over conductance. So it will be curly Vd over curly Id. And now this can also be written as delta V over delta I. Now what is the difference? I hope you know that when the delta represents very, very, very small deviation, and this delta represents a small deviation. So this is for a very, very minor change, and this is slightly a greater change than that. So we'll use this term also here. Okay, just to give you an idea that the resistance delta V over delta I, depends on where is the operating point. Now if your operating point is here, the value of RD will be different, and if your operating point is here, the value of RD will be different, because you can see RD is delta V over delta I. Now here delta I is very small. In this case, delta V is small and delta I is very large, so they have different values. And now let's do an example. Consider the circuit in figure 4.14. For the case when R is 10 kilo. So this R is 10 kilo. The power supply voltage V has a DC of 10 volt on which is superimposed a 60 Hz sinusoidal of 1 volt peak. So as we discussed earlier, that this DC volt is actually taken from a rectifier circuit. So we have a ripple which is 1 volt peak and it has 60 Hz of frequency, this part. So it is 10 volt DC plus this ripple. The signal component of the power supply voltage is an imperfection of the power supply design, and it is known as power ripple. Now what we have to do is calculate the DC voltage of the diode and the amplitude of the sine wave signal appearing across it. Okay, so this is where we're going to emphasize this knowledge here, that we can work separately, calculate separately for the DC and calculate separately for the AC. Now if you look at the circuit, this is the overall circuit. This circuit is for DC and this circuit is for AC. Now look here, the voltage here is the AC DC, this voltage here is purely DC, and the ripple source, we are representing it separately as Vs and with this resistance, and then the diode resistance RD. So this is for the small signal. This is small signal equivalent circuit. Now for the DC voltage of the diode, simple, we'll just use this formula. Considering the DC quantities only, so this figure, sorry, Vd we are assuming to be 0.7 volt. Here it is given that the diode have a 0.7 volt drop at 1 milliampere. Here we don't know how much current we have, but we are just assuming it to be 0.7, and we'll see if this is valid or not. So ID is, this 10 volt minus 0.7 divided by the 10 kilo resistance. So ID is 0.93 milliampere. And this is very close to 1 milliampere. So 0.93 is very close to 1 milliampere. And 0.7 volt is given for 1 milliampere. Therefore, our assumption is correct that Vd is approximately 7 volt. So ID we have calculated to be 0.93 milliampere. So this is the DC part of the analysis. Okay, now let's see the B part, that is we have to find the amplitude of the sine wave signal appearing across the diode. We have known this relation. So from here we find the diode resistance or incremental resistance. RD is Vt over ID. Vt we know is 25 millivolt, and ID we calculated in the last slide. This is 0.93 milliampere. So RD will be 26.9 ohms. Now the signal voltage across the diode can be found from the small signal equivalent circuit of this. So for the signal voltage or the AC voltage, we'll just use the small signal model, that is the AC voltage appearing, the resistance and the diode resistance. And note that Vs or the AC signal actually has 1 volt peak. That means if this is the average point, then it is 1 volt up. So we can say that Vs is 1 volt, the peak voltage. And Vd is corresponding signal across the diode. So this is the Vd across the diode, which is the AC signal. So we can find the peak of this. Vd peak is by this formula, the total voltage, that is 1 volt peak applied and divided by this circuit multiplied by Rd. So Vs is 1 volt peak, Rd is 26.9 ohm. This is 10K divided by 10K plus 26.9. So Vd peak is 2.68 millivolt. And finally we note that since the value is quite small, now this value is very small, so our use of small signal model for the diode is justified. So remember we had said that the diode voltage has to be very, very small, less than 5 millivolt. So this is fine. So we can use the approximate model which we have done here. Okay, and now we'll do a little example. Find the value of the diode small signal resistance Rd at base current of 0.1 milliampere, 1 milliampere and 10 milliampere. So these are the operating point currents or the base currents. Very simple, we just use this formula. From here we know that Rd is Vt over Id. Vt we know is 25 millivolt. So for Id is 0.1. So for this one, 0.1 Rd will be Vt over Id. Vt 25 millivolt, Id is 0.1 millivolt, so it is 250 ohms. And for the other IDs, when ID is 1 milliampere, the same, just we change the current here, so it will be 25 ohm. And when ID is 10 milli, it will be 2.5 ohms. So you can see that the resistance is changing with the change in diode current or the operating point. So I hope this gives you an idea as to how to solve this type of a problem.